One more example for related rates that had to do with the volume of a cone. And so this is an example that I had hoped to do in class today on Friday, but I just didn't get the chance to do it. So I'm going to do it now. Water pours into a conical tank of height 10 meters and a radius 4 meters at a rate of 6 meters cubed per minute. At what rate is the water level rising when the level is 5 meters high? Let's walk through our process for doing related rates. We need to identify variables. And actually, before we even identify variables, let's draw a picture. So we have a cone, and we know some things about this cone. The cone's height, like the total height, is 10 meters. This is a pretty big cone, pretty big tank. And we know that the radius is 4 meters. So those are fixed values, like that's just the size of the cone. Let's kind of take a look at our variables of what we have. It says that it's going at a rate of 6 meters cubed per minute. So you have to ask yourself, like, what is changing 6 meters cubed per minute? Well, meters cubed clues me in that it's volume. So I know that dV dt equals 6 meters cubed per minute. At what rate is the water level rising when the level is 5 meters high? So at what rate is the water level rising? Well, if the water level is rising, I'm going to come back over to my picture here. Let's kind of pretend that this is water. So I guess there's some kind of, hose or something that's filling up this tank, and the water level is rising. Let's call this H. If I'm wanting to know the rate at which the water level is rising, that is going to be dH dt. That's what I'm looking for. And I'm wanting to know specifically when the level is 5 meters. So I'm wanting to know dH dt at H equals 5 meters. So of course, we're going to need a formula to relate all of these variables. And because I'm dealing with volume here, you can kind of assume we're going to need the volume formula. So you probably don't know this off the top of your head, but you probably do need to know this. If you go to the back of your book and look at the formulas, you can see that the volume of a cone is equal to 1/3 pi h r squared. All right, this problem is different than any of the ones that we've done so far because the formula that I'm actually starting with has 3 variables. It has volume, it has height, it has radius. I don't really know anything about the radius as far as the rate of the radius changing or anything like that. So if I were to take the derivative of this, I would end up having to do the product rule, and I would end up having a dH dt and a dr dt. And there's just nothing in my information that tells me anything about dr dt. So before I even take the derivative, I need to figure out a way to get rid of that r. So I do know something about r. If I look at my original cone, wouldn't you guys agree if I kind of made a proportion here? If I was doing the ratio over the height, it would be 4/10. Okay, I know this is new, but this is how you would do these problems. The cone problem is really, really typical, and the way you're going to have to deal with it is with a ratio. So r over h equals 4/10. We can just see that from looking at my original cone. So I can actually solve for r. So basically, whenever the height no matter what the height is, the radius is always going to be 4/10 times that height. It has a proportional relationship. So now that I know what r is, let's actually take this and plug it right here in the place of r. So I'm going to have v equals 1/3 pi h 4/10 h squared. And let's go ahead and reduce this. Simplify it. 4/10 squared is 16/100. So we have 1/3 pi h 16/100 h squared. And this gives me, I'm going to go ahead and multiply. Since notice all these variables are right next to each other, so I can multiply them. I'm going to go ahead and multiply all of them, and I'm going to have 16/300 pi h cubed. Okay, this is going to be much more helpful. Now I can continue with my process for related rates. I identified my variables. I wrote an equation that related the variables, and really the only variables I wanted to relate were v and h. Now that I have those related, I can take the derivative, just like normal, with respect to time. So this is going to be dv dt equals, remember that this 16/300 times pi, like that's actually all a coefficient. So I'm going to like multiply the 3 down and subtract 1 from my exponent. I can simplify this. This is going to be 16/100 pi h squared. That's dv dt. I left off something. Do you see what I left off? I'm taking this with respect to time. I took the derivative with respect to time. So dv dt equals 3 times 16/300 pi h squared times dh dt. I left off my dh dt term. That's no bueno. I'm going to reduce a tiny little bit here. 16/100 pi h squared dh dt. Now we're at the point where we need to plug in some variables. So if you want to go ahead and get the dh dt alone, you could do that. Or you could go ahead and plug in numbers and then get it alone. It's really not a big deal. Yeah, it's just really not a big deal. So let's maybe plug things in. I don't know. It doesn't matter. We actually have dv dt. If we were to look back at the previous slide, or you guys look back at the top of your paper, you'll see that dv dt was the 6 meters cubed per minute. And I'm wanting to find dh dt when the height is 5. That was the other variable that I had. Okay, I'm going to go up here because I'm running out of space. This looks a little bit crazy. But if I were to, I'm actually just going to write it all the way out. It's going to look ugly, but basically I'm going to divide both terms, both sides, by the 16/100 pi times 25. And when I do that, I get approximately 0.48. And that's the rate that the height is changing, so that's meters per minute. So DHCT is approximately 0.48 meters per minute when the height is 5 meters. I'm going to go ahead and specify that. So So there's the answer right there. I guess the main thing that I wanted you guys to see with this problem, there are 2 cone problems on your homework, and that is not a mistake. Cone problems are very, very common on the AP exam, so we want you to be familiar with them. The key to the cone problems is that whole ratio thing. You know, if the height is 6 and the radius is 2, then you can set up a proportion, radius over height equals 2 over 6, and that's a third. And you'll have to solve for the radius, so the radius would basically be 1/3 h, and you'll have to plug it in. So this is not the same problem. This is just another example of kind of how you would have to start off. So watch out for those cone problems. You could definitely use this one as an example, and I'm not 100%, I don't think there's one in your book, but if you were to Google related rates cone problem, I can guarantee you will find more videos on it if you need help with it. Please do your homework this weekend. Please walk through the steps. For every single problem, even if you get stuck, you should be able to identify the variables, write an equation, and take the derivative. Honestly, if you get that far, I would bet that you could solve it. So have a little faith in yourself. Don't be afraid to make mistakes. Just give it a try, and we will reconvene on Monday. So I hope you guys have a great weekend, and I will see you Monday.